Hi, I'm Zeynep Ergin. I'm a freshman electrical electronics engineering student in Bilkent University. Today, I will be sharing the results I have obtained from my Physics 101 project, which is titled Determination of Spring Constants in Single, Series, and Parallel Configurations. The aim of the experiment was to investigate how configurations of spring affect the spring constant K, which determines the spring stiffness.
I calculated the theoretical spring constants using Hooke's law, which is this formula. To calculate the force F applied on the springs, I calculated the weight of the object due to the Earth's gravity using this formula. I considered the G value as 9.8 meters per second square. And lastly, to calculate the displacement of the spring, I measured the spring's initial length and final length and subtracted these values. With this equation, we can find the effective spring constants for each configuration. Using these formulas, I have also calculated the effective spring constants for springs in series and parallel, later to compare these theoretical values to experimental values. The equipment I have used for the experiment was 2 springs with the same spring constant, 3 metal objects, each are 100 grams, 2 hooks, a mess hanger, a 50 centimeters ruler, a balance, and a spring stand. First, I measured the mass of the mess hanger to include its mass in the experiment since it also applies a force on the springs. Then I placed a single spring to the spring stand and measured its equilibrium length using the ruler. I attached a mass of 100 grams to the spring and measured the final length. I repeated the same procedure for 200 grams and 300 grams of masses and recorded all values. Then, I connected the springs end-to-end, forming a series configuration. I measured the initial length for this setup and measured the final length of the springs after the masses were hung. After that, I connected the springs side by side, forming a parallel configuration. I had to use a pencil to hang the mess hanger, and I measured the initial length for this setup too. Then I repeated the same procedures. I have collected these data sets on the screen from the measurements. Then, I plotted the force applied on the spring versus displacement graph for each table using PHYS101. The slope of the best fit line of the graphs gives the effective spring constant K for each configuration. Later, I compared the experimental spring constants with theoretical spring constants, which were 120 newtons per meters for a single spring, 60 newtons per meters for springs in series, and 240 newtons per meters for springs in parallel. I have obtained 8.73, 12.25, and 15.88 percentages of error. The reason for these errors might be due to human errors, such as parallax and measurement errors, and errors caused by materials and setup. Also, in this experiment, I considered G as 9.8 meters per second square, which might not be the accurate value, and this might have caused an error. To reduce these errors, more precise measurement tools can be used, and the springs can be aligned properly to avoid misalignments. If we ignore the errors occurred in the experiment, we can conclude that there is a proportionality between the force applied on the spring and displacement from the equilibrium position. The force applied divided by the displacement gives us the value of effective spring constant for each spring configuration, validating the Hooke's law. Additionally, spring constant K varies in different spring configurations.